Hello everyone, and welcome to the class. So this is a special class which you all can attend on my YouTube channel. The link I've already shared, and I welcome you everyone who is here to present to attend the class. So in the class, I wasn't able to solve many of the problems completely, and that is one of the reasons why I'm making this video. So I'll be solving problems from some of the previous year question papers. 2018, you can see this is a paper. There are a lot of papers available to me. And from these papers, I will be trying to solve a lot of problems. Okay. So mostly we'll be solving problems which are based on the velocity and acceleration diagrams. Okay. Now I've already copied all these questions over here. And let's begin them one by one. I'll start from the beginning, the first one. And this here is the problem statement, and we'll be using AutoCAD to draw the diagrams. I'll be using most of the times. I'll be using the instruments, drawing instruments, geometric instruments, for showing you how exactly you can use your actual instruments to complete the diagram. And the paper size I'm going to be using in AutoCAD will be the A4 sized paper, which is your standard Xerox paper that you use for printing. Okay, in Xerox. You can see this is the paper in use. This is a standard A4 sized sheet I'll be using. And as you can see, there are these are all the virtual instruments that I've created, which function very similar, very similar to your actual instruments. We have a compass for which I can rotate and change the radius. I have a mini drafter which I will be able to rotate to whatever angle I want. Okay, if I want exact angle, I will be able to use this scale over here and get that angle. Then I have a protractor here, which I'll be able to use to take the different angles from the right side as well as from the left side. And I also have a simple scale which can be used very similar to your roto scale, roller scale, okay, which is a scale which can be set parallel to a particular line and can be moved perpendicular to itself like this to get parallel line anywhere in the paper. So without making much delay, let us begin. So let's come back to our problem statement, which is over here. So we'll have to do a lot of writing, which I will be doing over here in this interface. And once the writing is done, wherever we need the diagrams, I will be switching to AutoCAD to solve this, solve the diagram based problem. Okay, so let me just set this off the screen so that you'll be able to see in the left the matter which I have written, and on the right you will be able to see the diagram that we are drawing. So coming to our first problem, we have here dimensions and configurations of 4-bar mechanism shown over here. They're given as follows. All the lengths are given, and the angle A P1 P2 is given as 60 degrees. The crank P1A has angular velocity of 10 radians per second and angular acceleration. So this question is going to be a little more complicated than what we solved in the class, because this one has angular acceleration also involved. Okay. So both of these, he is telling that both of them are clockwise, and he's asking us to determine the angular velocities and angular accelerations of P2B and AB, and the velocity and acceleration of the joint B. So since this problem involves angular acceleration, we'll solve it a little later. Okay, so we'll come back to this and solve it a little later. Let us take up a slightly simpler problem to begin with, so that once we are thorough with the velocity diagram and how to draw it, we'll go on to include a little more elements that of the angular velocity into the same diagram to be able to draw it. So let's take up this problem. We have in the engine mechanism, crank and connecting rod lengths are 50 and 250. The center of gravity of the connecting rod lies at 100 mm from the crank pin. So when the crank is at 45 degrees from IDC, inner dead center, while rotating in clockwise direction at 500 rpm, find the velocity of the crank. Okay, so this one is a comparatively simpler problem. So we all know that a slider crank mechanism is going to be like this, wherein we have a crank, okay, and then we have a connecting rod, which is also called as the coupler. Okay, a connecting rod or coupler will be like this, and then we will have a slider. Okay, and the slider will be moving on a straight. It will be sliding to and fro on a straight surface like this. Okay, so this one here is the slider. Okay. So what he's telling, he's telling inner dead center. Fine. So inner dead center is when the slider is on the inner side. This is called as the inner dead center, and when the slider is moving to the extreme, that is called as the outer dead center. Okay. So he's telling from the inner dead center, the crank has rotated an angle of 45 degrees. Actually, inner dead center and outer dead center, there could be a little of confusion between these two positions. Let us quickly do a small research to find out which one it is. What is IDC and ODC in slider crank mechanism? Right. Having a clarity about this is very essential, because when we are looking at the crank point of view, the crank is inner dead center over here. When crank is on the inner side, the piston is on the extreme side. So let's quickly clarify what it is. So inner dead center and outer dead center are the two extreme boundary positions of the slider stroke. So inner dead center definition, this is the position where the slider is at the closest possible position to the center of the crank. Okay, so yeah, so whatever definition I have given, that is correct. So when the slider is towards the crank, that is called as the inner dead center, and when the slider is towards the outer extreme maximum distance from the point of rotation of the crank, that is when we call it as the outer dead center. Okay. So this can also be called as the top dead center and bottom dead center when the slider crank, when the piston is moving in the vertical direction. Right? So when the piston is moving in the vertical direction up and down, this top dead center and bottom dead center is how we can call it. Okay, so let me just place it on the side here. So when the piston is like this, the coupler will be like this, and the crank will be like this, and of course the crank will be rotating about this center, and the piston will be moving up and down. So we'll have some kind of cylinder which is fixed here, and the crank is going to move up and down. So these are the definitions of inner dead center, outer dead center, top dead center, bottom dead center. Yeah. So coming back to the question, so we have been told that the center of gravity of the connecting rod is 100 mm from. Okay, so we'll come with that. Okay, so the position is that the crank is at 45 degrees from the inner dead center, rotating in clockwise direction. So that means it is rotating in clockwise direction, and from inner dead center. Inner dead center is when the piston is on the extreme lower side. When the piston is on the extreme lower side, the crank will be in this position, right? The crank will be in this position, and the coupler is going to be in straight line, and the slider will be somewhat like this at inner dead center. Okay, so from the inner dead center, when the crank rotates like this, this is what he is telling, that is at 45 degrees the inner dead center. So from this position we will have to take an angle of 45 degrees. From here we'll have to draw the coupler, and accordingly we'll have to complete the diagram. Okay, so let's draw a rough diagram of this first. And so we'll have to take this as the reference. Yeah, this point we'll have to take a reference and draw an angle of 45 degrees. Okay. And, then next we will have to take a coupler. The coupler we will have to draw like this, and the slider will be somewhat like this. Okay. So this will be at the center, and of course the slider is going to be sliding on a horizontal plane like this. Okay. So this is the position, and this angle is 45 degrees. What are the lengths? So the lengths are given as crank and connecting rod of 50 and 250. So 50 mm is the crank length, and the coupler or connecting rod is 250 mm, which is given over here. Yeah. Then the center of gravity of the connecting rod lies at 100 mm from the crank pin. Okay. Where is the crank pin? Okay. So 100 mm from the crank pin on the connecting rod itself. This point here is called as the crank pin. Okay, pin. So from the crank pin, we'll have to take a point. Okay, so let's call this as O, this point as A, this point as slider. So yes, and let us call this point as C, the center of gravity. And he's telling the center of gravity is 100 mm. So from here. So AC length is giving as 100 mm. Yeah. And this length, the coupler length is going to be the total length of the coupler. Okay. So this is the diagram we need to draw. So first of all, we need to start with the position diagram. Okay. So let's take our scales and keep them horizontal. Okay. We'll have to take your scale. Place it here. Yeah, you will take a scale and place it parallel to the bottom boundary of the top order. Then you will have to roll it. You'll have to roll it upwards to a convenient distance like this. Okay, and the crank is 50 mm, 5 centimeters we can easily draw, but 250 mm drawing this is going to be slightly difficult. So in order to make it slightly smaller, let us take a scale of 1:2. Okay. Scale we will take it as 1:2. This we will do it for the position diagram. Okay. So for this, for every time we take a scale, we'll have to draw a table wherein we'll have to take length. Sorry, first let us take the name of the link, and then actual length, and then the drawing length. Yeah. So because we have taken the scale as 1:2, all the lengths we will have to make it half in the drawing length. So let us start. So first is the crank length, which is 50 mm. Sorry, crank length, let us write the name. The name is OA. Actual length of that is 50 mm, and its drawing length we will take it as half, so we will draw it as 25. The next length is AS. The total length is 250 mm. That's what is given in the problem, but we will actually draw it as half of this, so we will draw it as 125 mm. And then we also have been given the length AC. AC actual length is 100 mm. But we will have to draw this as half of it. So let's take that as 50 mm. So this table over here we will be using to make the diagrams. Okay. So, save some space for moving it here. So here. So let's just separate the width and see what it has. Okay. So we have the table which gives us all the lengths that we need to draw for the position diagram. So let us begin drawing them over here. Okay. So first of all, we'll have to take a point somewhere. Okay, so let's take a point over here. And since you can see all the position diagram is on the bottom side, so we can just take this point at the top. Okay, and let's name it as the point O. So because this is the position diagram, we'll have to name all the points with capital letters. Okay, and next we will have to use our protractor. Okay, this protractor we will have to put it reverse. Okay, first we'll have to draw a horizontal line and put our protractor like this, and the angle we need to measure it from the left side. So your protractor will have measurements from both the sides, from this side as well as from this side. For my virtual protractor, you can see I have this flipping button with which I can flip it. So 0 degrees has to come on the left side. From here we'll need to measure the angle. So let's measure the angle as 45 degrees over here. Okay, and then let's draw the length. Okay, so this length has to be equal to 25 mm as I've shown it over here. So let's take quickly our scale, keep one corner correctly, rotate the corner to make it like this, and then now we'll have to mark it at 25. 25 means 2.5 centimeters. So this is where we will need it. Okay, so this lane we will need only till here. So this is our clank length. Next we will have to draw a horizontal line. So let's quickly take our scale right here, and we will have to draw a horizontal line like this. Yeah. Also we will need to make this as axis line. So this line we will have to make it as axis line. And next thing, we will have to take our compass and the scales. Okay, let's take our scale. Let's take our scale, and let's also take our compass. Okay, we'll have to take our compass over here, and the length that we need is 250 mm. So let's take 250 mm. 250, not 250 mm. Here while drawing we'll have to draw 12.5 centimeters. So 12 centimeter 0.5. This is the length we need to mark. So we'll have to take the center point and keep it over here, and we'll have to draw arc from this. Okay, so this arc we will not need the complete arc, we will just need to draw this much arc. Okay, we just need to draw this much arc over here. Okay, so wherever it intersects our line, that is where we will have our center point of the slider, which is yes. Okay, so let's quickly name it with capital S, of course, and then this point over here is our point E. So let's quickly write it as E. So this completes our position diagram. This completes our position diagram. Once the position diagram is done, we will have to proceed to draw the velocity diagram. So for velocity diagram, first we will have to calculate some of the velocities. Okay, so let me quickly just take all this. Move it down. Okay, let's move it to the other side, so that we'll have space for going on for the velocity. So now for the velocity, okay, so we will also need the position diagram. So we quickly take the position diagram. like this. Let's move it over here. Okay, so we'll need the position diagram for the velocity. Okay, so he's telling that 500 rpm is the clockwise rotation. The crank is rotating at in clockwise direction at 500 rpm. So rpm value has been given 500 rpm. So this is the rpm for OA, which is the crank. Okay, so here once again we'll have to draw a table called the velocity table. Okay, so first length that we are taking is the link length. Okay, so let's first write down the notation. Okay, let's say rotation, then velocity, okay, and drawing length. Okay, so these three things we will need here. So the first velocity that we need to find will be the velocity of A with respect to O. Velocity of A with respect to O. Okay, and the velocity we will write it as OA, and this will be equal to omega times OA. Okay. So first we will have to find omega. Let's quickly find that omega over here. Omega formula is 2 pi n by 60. This is the formula for omega. So let's quickly go to our calculator. Okay, right, so in the calculator we'll have to feed the values. Okay, so 2, first we will have to take 2 into pi, 2 pi into n value we know it is given as 500. Instead of taking into a point, so this divided by 60. So omega value we are getting it as 52.359, which will round off to 52.36. 52.36. This will be in radians per second. So now we know the value of omega, and we will have to now find this velocity. Okay, so omega value 52.36 into the length OA. Now when we are taking the length OA here, we should not take the length that we have drawn. We should take the length that is given in the problem. This you have to be very careful, because the velocity will depend on the actual length, not on the drawing length. Drawing length we have just drawn to get the idea about the different orientations. Orientation means the angles at which the different links are inclined, and these angles will be very helpful for us to draw the velocity diagram. Okay, so 52.36, that is omega, and OA length, that is 50 mm. Now this 50 mm we will need to convert this into meters, because we will use the value in meters only. Okay, so milli means 10 power minus 3. 10 power minus 3 when you multiply with 50, you will get 0.050 meters. So 0.05. Okay. So this will give us the actual velocity. Okay, let's go back to our calculator and quickly find this. So we have 52.36, multiply this with 0.05, that will give us the velocity. We're getting 2.618, we can round it up to 2.62, 2.62, and this will be in meters per second. Okay, this will be in meters per second. So this velocity we will have to actually draw on our paper. Okay, so once again you can see that the paper size that we have is A4 size. It has limited amount of space, so we have to ensure that whatever velocities we are drawing will fit up on this paper. Okay, so 2.62 meter per second is the velocity that we got, and 2.6 centimeters we can easily draw. on 2.6 centimeters we can easily draw. You can see 2.6 centimeters is only this much, but this is actually very small. So let's do one thing, let's multiply this with 2. Okay, so the drawing length we will take it as 2 times of the velocity. Okay, so that way we can draw it more neatly. So 2.62 when doubled we get 5.24. Okay, so let's round it off to 5.25 mm. Sorry, not mm, we'll take it in centimeters. Okay, so this is the drawing length we will draw. And to draw this, we should also we should also know the direction. Okay, so let's quickly note down the direction. So how we will get the direction of this? You can see here, over here, just quickly change this one. So the velocity of A with respect to O, will need to be perpendicular to the length OA. Okay, that's how we will find the velocity. Okay, so here I will have to quickly write down perpendicular to OA. That's how we will need to take it. Okay, so let's quickly go back to our problem. Okay, so let's get to our drawing sheet, which is not opened, and we will have to take perpendicular to OA. So let's first take our protractor. And keep it this line. Yeah, we'll have to keep it like this, and we will have to take it perpendicular to this. Okay, so I'm just quickly drawing a line which is at 90 degrees. So we can see that to this we have taken an angle of 90 degrees, and this will be the direction along which we will have to take the velocity 5.25. Okay, so next step for you will be to take your scale, take your roller scale, keep it parallel to this line, and then roll it at a convenient point. So the starting point we will take it about somewhere over here, and from this point we will have to draw a line. Okay, initially when you take the line, you can take it of any length. We will be, because placing it exactly at 0 degrees will be a little problem. So first draw a line of any length from the reference point. The starting reference point for us is going to be the point O. Now this one we'll have to write it with a smaller alphabets to avoid confusion between the velocity diagram and the position diagram. Okay, so this is the point. Now the length we know, the length that we have to draw is 5.25. Okay, so now let us take back our scale. And first we will keep this point over here, and we will have to rotate it here like this, and we need a length of 5.25. 5.2 is here, 5.3 is here, 5.25 will be exactly in the middle, between 2 points, middle of these 2 points. Yeah, so that's our point. So this point that we get here, that this must be called as A. Yeah. And as you can see here, the length of velocity that I'm writing here is OA. So from O to A, that is the velocity. Okay, so we will only need this point till A only we need it. Extension we will not need it. So once we have drawn that, that is the velocity of OA, A with respect to O, velocity of A with respect to O. Next, we know that the velocity of S with respect to O in direction we know it. Okay, because this will always be sliding in this particular direction, its velocity will be horizontal. So next what we need to do is we need to take our scale. We need to arrange it like this, and we will have to move it, we will have to roll it till it passes through O. Okay, so we'll have to roll it till it passes through point O. Okay, once it passes through O, let's quickly take a line. Again, this line you can take it of any length, because we don't know in which direction it is moving, neither do we know what is its length, because we don't know what is the velocity of S yet. The only velocity that we knew, we have already drawn it both in magnitude as well as direction. Now once we have drawn this parallel to this, next we will need the velocity of A with respect to S. Okay, so let me just quickly write those velocities here as well. The velocity of S with respect to O, velocity of S with respect to O. Now for this we will know the direction. It will be parallel to O S. It will be parallel to O S. Okay, and then the next velocity we will need is this away. Okay, so this is just the rough diagram that we have taken. So next velocity we will need is velocity of point E, or else velocity of point S with respect to point A. Now both S and A are moving, and we know that this is a kind of relative velocity, and this relative velocity will be definitely perpendicular to AS, perpendicular to AS. Okay. So the notation here for O, the velocity of S with respect to O, will be OS. So you can see that it is passing through the point O, and the notation for this will be AS, and you can see that it is passing through A. Okay, let's come back to here our diagram, and you can see that we have already drawn the line for OS. It is already passing through O. We don't know which side S is located, so we'll just keep it like that for some time now, and then we will have to draw the line AS. Now the line AS, we have written it is perpendicular to AS. Perpendicular to AS means over here. Let's quickly take our protractor. And keep it at some reference point. Yes, and once again we will have to draw a perpendicular. Okay, so first let me place a point here, and then from that point I need a perpendicular. Okay, once I have drawn the perpendicular, let me just remove my protractor. Right, so this is the perpendicular that we needed. Once the perpendicular is in place, we will have to quickly take our roller scale, place it parallel to this, and then we will have to roll it. We'll have to roll it till it meets the point A. Till it meets the point A. It has to pass through the point A. Okay. Once it passes through the point A, we just have to draw a line. Yes. Okay. Then this is not longer blended, so let us remove it. So we can see that we have drawn these two, not knowing which side the point S will be. Okay, but we have somehow got the intersection of the two lines that we have drawn. Okay, and that point we will have to name it as the point S, small s. Okay, this point we will have to name it as small s. Okay, so this gives us the velocity diagram. Okay. Okay, so if you want, you can just make it dark, because this is the diagram that we need. Yeah. Here also, wherever the link lengths are there, we can make it darker. Yeah. This reference point we had taken only for getting the perpendicular line. Yeah. So this here is the velocity diagram. Let's quickly write that. Okay. Velocity, and this here is the position diagram. Okay, so position diagram, velocity diagram. Okay, now by measuring this velocity diagram, we will be able to get the other two velocities. Okay, so let us first measure the length OS. let's measure the length OS. Okay, so when we measure the length OS, we see how much is it. This is almost 3.2. So 3.2. So OS length we found it as 3.2 centimeters. So this is the drawing length that we have got. We have got the drawing length. So for getting the drawing length, what we had done, we had multiplied with 2. So now to convert it back, because we are coming from right side to left side, we will have to divide it by 2 to get the length. So okay, so when we divide this 3.2 by 2, we get 1.6, and the unit that we get here will be meters per second. Okay, so this is how we can convert drawing length to the velocity. Every time we want to convert drawing length to velocity, we will have to divide the scale. Okay, and every time we want to convert meter per second, the velocity, into a drawing length, we will have to multiply with the scale. Okay. So now that we have the velocity of the slider, what is asked in the problem, let's go back. You can see he's asking the velocity of the slider. Yeah, velocity of the slider. So velocity of the slider we have found. So this is the let us mark it as a bit. So a bit we were able to find. Yeah, and the velocity of center of gravity of the connecting rod. That is also one thing that is asking. Yeah. So how to find the velocity of the center of gravity of the connecting rod? So we know that the center of gravity of the connecting rod is located at a distance of 100 mm from the distance of crank pin. So let's come back to our sheet. And we will have to find the point center of gravity. Center of gravity is from the crank pin. It is located at a distance of how much? It's located at a distance of 100. Okay, so 100 mm. But we can see in this table, the drawing length we have taken a scale of 1:2. So we will have to mark it at a distance of 50. We'll have to mark it at a distance of 50. Let's take 50. 50 means that will be 5 centimeters. Okay, so this is the point center of gravity. Okay, and let's quickly name this point. So this has to be named as capital C. Now he's asking us what is the velocity of center of gravity of the connecting rod. So this, let us take it as the B bit. So in order to find the velocity of the center of gravity of the connecting rod, first we will have to find the point for center of gravity on the velocity diagram. Okay. How to find the point C? That becomes over. So this we have not been asked, so let us put it aside for now. First let us find the velocity of center of gravity. Where center of gravity is C, he is asking us with respect to the fixed point O. Okay. So this is the velocity that we have been asked to find. So on the diagram, this will be OC, small OC. Okay, this is what we need to find. And how to find this? Fine. So this we will have to take it proportional to OS. So OC will be small OC should be taken as proportional to capital OC. Small OC should be taken proportional to capital OC, which means this distance small OC by OS should be taken as equal to capital OC divided by capital OS. So this relation we'll have to use to find the length OC. Okay. Now OS is the length. We already know. Okay. OS is the length we already know. Okay. Actually, this length OS is the length which we already know. So let's go ahead and take it. So OS length is 3.2. OC, small OC length we don't know. Small OC length we don't know. OC length we don't know. That's what we need to find. OS is the length that we know. That is 3.2. So let us substitute. This should be equal to capital OC. Capital OC that we know. Capital oh sorry, not OC, this is C with respect to O. OC is the length we need to find, but for finding the OC length we will have to be careful. This is not the thing. So to get the point C, we will have to take the length, AC. So the length AC should be taken proportional to capital AC. Okay, so AC divided by capital AC by AS, AC by AS should be equal to capital AC by capital AS. So this is the relation which will ensure that the lengths are in proportion. So this is the proportional length we need to take. So capital AC is something we don't know, keep it as it is. Capital AS, we know it. Capital AS, we know it. Capital small as is what we know it. We know it from the diagram. So how much is it in the diagram? Let's come back here. AS is this length. Okay, so this length we need to measure it. How much is that? So take your scale, keep the 0 at this point, keep it here. So AS length we are getting this is 3.75 because it is in the middle of 3.7 and 3.8, so 3.75. so AS length is 3.75 in the velocity diagram. Now AC and AS we have to take it from the actual measurements. So actual length AC is 100, and actual length AS here you can see that is 250. It's 250. Okay, so now we using this we have to find the value of AC. So AC will be equal to 3.75 times 100 divided by 250. So let's find that quickly using our calculator. Let's come back here. So let's take A by B. 3.75 into 100 divided by 250. That we are getting as 1.5. Yeah. So 1.5 centimeters is the length AC. So let's come back to our sheet. So in the sheet, from the point A, the point C should be taken as 1.5 centimeters. So 1.5 centimeters. So 1.5 centimeters. This is the point where we have to take the point C. So let's quickly name this as point C. So here we have to take small c, not capital. Okay. So now we have got the point C. So once we have the point C, we can see here that the velocity of C with respect to O, is given by this line, this point to this point. This is the line which gives us that measurement. So let's quickly take our scale. Keep it parallel to the point OC and measure it. How much are we getting? 4.1, between 4.1 and 4.2, so 4.15. So OC length is 4.15 centimeters. So this is what we have drawn. We have taken it from the diagram in centimeters. So this we will have to convert it back to meters per second. So to convert it back, we will have to divide it by 2. So divided by 2, what do we get? So let's come back here. So 4.15 divided by 2, we get 2.075 meters per second. We can round it off to just 2.07 or 2.08 meters per second. So this is the velocity of the point C, which is the center of gravity of the connecting rod, with respect to O, which is the fixed point. And we have been asked to find the absolute velocity. That's what we have found. So B bit also has been found. So B bit is found over here. Next, is he also asking anything else? Also find the angular velocity of the connecting rod. Angular velocity of the connecting rod is asking. Fine. The angular velocity of the connecting rod, you can write it as omega. Connecting rod is AS, omega AS. And the formula for this, we can take it as the velocity of A with respect to S divided by the length AS. That will give us the angular velocity. So velocity of A with respect to S or S with respect to A, both are the same. So this is what we have been asked now to measure. So let's go back to our diagram and measure the length AS, small as. So let's we have to now measure the length A. We'll keep this scale, you have to keep it here, and yes, the AS length we have to measure. AS length is how much? A to S, we are getting 3.5, 6, 7, 3.7 and 3.7 and 3.8, in between 3.7 and 3.8, so 3.75. So 3.75 centimeters, we got this as the length. Once again, we have to divide it by 2 to get the actual velocity. So divide this by 2. Let's quickly go back to the calculator. 3.75, we're getting 1.88. So let's round it off to 1.88 meters per second. Yeah, meters per second. 1.88 meters per second. So this is the velocity of S with respect to A or A with respect to S. Okay, only the direction is going to be opposite. The value is going to be going the same. Okay, so 8.88. So this we have to substitute over here in this formula. So, okay, 1.88 divided by the length AS. So when we are talking about AS length, we will have to take this length, of course, convert this into meters. So divide this by 1000, we get 0.25 meters. So that's the length we need to take over here. Okay. So now do this quick calculation. Let's first going back to calculator. Do this 1.88 divided by 0.25. So this gives us 7.52. 7.52. Now this is because this is angular velocity. This is in radians per second. So this is omega of AS, and this is our third bit. This is our third bit answer. Okay. So you can see we have solved the full problem. Okay. Let's enclose this velocity table neatly here. Okay. So this is how we need to solve the problem. First, we need to draw the position diagram for getting the correct directions. And once we have got the correct directions, okay, once we have got the correct directions, which you can see over here on the sheet. It's a bit stuck. Sorry. I don't know, sometimes it just gets stuck and I have to close it. Let's save and close it. Open it back. Okay. So, so this position diagram, let's remove the scale. So we have the position diagram, we have the velocity diagram, and we have taken all the measurements and written it over here. And we have found whatever he is asking us to find. Okay, since he is not asking us to find any acceleration, so the problem is only up to here. Both these diagrams you need to draw in your sheet, and if you are provided with the drawing sheet, you can solve this problem in your actual drawing sheet using all your instruments, and attach that drawing sheet with your answer script. If, however, your examiner is not giving you the drawing sheet separately, you will have to do away with your answer sheet itself. And doing it on the answer script is going to be slightly difficult. You will need a lot of practice, how to use your roll scale, how to use a protractor, and all of the drawing instruments. This is something that you will need a good amount of practice with. Unless you have this practice, you will not be able to draw it correctly. Okay, so that's how we solve this particular problem. So the easy problem having done with this, let's go and solve a problem of 4-bar mechanism next. Here we have a slightly simpler problem on 4-bar mechanism. Let's solve this one. Let's quickly write down what is the given data over here. So given data. Okay, so first he's telling the crank is AB. So crank length is AB, and it is rotating. Rotating means the rotational speed of the crank AB. The rotational speed of the crank NAB is being given as 360 RPM. Okay. Then the link lengths have been given. AB length has been given as 200 mm. AB length has been given as 200 mm. BC length has been given as 400 mm. CD length has been given as 450 mm, and the AD length has been given as 600. Now AD length is the fixed one, so AD is the fixed one. Let's fix this. Yeah, AD is the fixed one. At an instant, AB is at right angles to AD. Right angles to AD. That means the angle DAB, the angle DAB is 90 degrees. Okay, this is the position. This is defining as the position. Okay. So next we'll have to quickly do the position diagram, for which we will have to take some drawing scale and draw it. So 200 mm means 20 centimeters. The largest distance here is 600 mm, which means 60 centimeters. Now naturally this is very difficult to be drawn on the paper, so we will have to take some scale so that the diagram is large enough to avoid a large amount of error to take in, but small enough to be able to, so that we will be able to draw it conveniently on the drawing sheet. Okay, so 12 centimeter is the length which I think we can draw easily on the drawing sheet. So this we will take it as 12 centimeters. This we will take it as 12 centimeters. So to make this into 12 centimeters, what is the thing that we have done? We have multiplied it with 2 into 2 by 100. Okay, so we have multiplied this with 2 by 100. That means 1 by 50. We have multiplied this with 1 by 50. So this becomes our scale. So the same scale we will have to take for all the lengths. Okay. So again here when we multiply this with 1 by 50, we get 4.5 into 2, we get 9 centimeters. This is 400. 4 times 2, that is 8 centimeters, and this becomes into 2 for 4 centimeters. Okay, so these are the drawing lengths. We have taken the scale and we have quickly found out the drawing lengths. If you want, you can put it in a nice table as well. So let's now quickly draw the position diagram. So first length is going to be AD, because AB. AD is fixed, not AB. AD is fixed, not this point. And so AD is fixed. So this is the length which is fixed. So AD length, let us draw. We will have to draw it as 12 centimeters. We'll have to draw it as 12 centimeters. Then to find the point B, we'll have to draw AB. AB, we'll have to draw is telling it has to be drawn at 90 degrees to find the length B, and the length AB we have to draw it as 4 centimeters. Okay, and then from B to C the length has to be 8 centimeters, and the length from D to C has to be 450, that is we have to draw it as 9 centimeters. Okay. So with these two we'll have to draw arcs, and by connecting them we will get this point C. Okay, so this is how we will need to draw the position diagram. So let's come back to our diagram. Let me take this time let me take the take it in portrait. Okay, since this it's just some general diagram, but we don't need this one. Okay, all right, so we'll have to first draw the position diagram. So let's quickly take scale. Okay, so we'll have to take our scale quickly and draw a length of 12 centimeters. So vertically you can see we need a length of 9 centimeters, so slightly more than 9 centimeters length we'll have to ensure that it is there, and at that gap we'll have to draw this line. Okay. So from here we will have to draw a length of 12 centimeters. So 12 centimeters. So this point here, these are the points. Okay. So what is the point? This point here we will have to take it as A, capital A, and this point here we will have to take it as capital D. Yeah. So this length is 12 centimeters. Next, what we'll have to do, we'll have to again take our scale. Yeah, and okay, first we'll have to take our protractor. So take a protractor, put it here at this point, and we need to measure the angle from the right side. So from right side we need an angle of 90 degrees. So for 90 degrees let's take a point. This work is done. Then let's take our scale, put here, and we will have to make it pass through this, and on this we will have to take a length of 4 centimeters. So let me take line and draw a length of 4 centimeters. Okay, let's keep this at. So this is the length of 4 centimeters. So this point that we get here we will have to call it as B. Okay, and the point C will be somewhere here. Where exactly? We don't know what that. Yeah, so to find where exactly, we will have to use our compass. We will have to use our compass. So let's quickly take compass. Okay, let's take our compass. Keep it on this scale, and now we need to take a length of 8 centimeters. 8 centimeters. So quickly let's take a length of 8 centimeters. You can see my compass has taken a length of 8 centimeters. So that 8 centimeters we have to mark it from point B. We have to mark it from point B. Fine. So keeping the length 8 centimeters constant, we'll have to mark an arc. Okay. So we don't need complete arc, we just need a part of this. So like this we'll have to draw an arc of length 8 centimeters. Once you are done with 8 centimeters, next let's again take it here. Next we will need a length of 9 centimeters. So let's take a length of 9 centimeters like this. So this 9 centimeter I have to mark it from this point. Okay. So somewhat like this. Okay. So when you mark an arc passing through this point, you see where this is how we will get it. And we don't need complete circle, so we need only this. Okay, so we can see that now we got the two arcs. No need to draw the arcs very big, you can keep them as small as possible. Yes, again, once you have the point, you just need to connect them. Okay, and this gives us the position diagram. So position diagram, all the links which are visible, we need to be drawn dark. Okay, so this is a point C. Now that we have our position diagram, the next step for us is to start getting the velocity diagram. Let's quickly start getting the velocity diagram. So first again let us draw a rough diagram of the velocity diagram, and after that we will go on to draw it neatly. So here, because the link AD itself is fixed, the link AD itself is fixed, AD is fixed. So both the points A as well as D will come, it will overlap in the velocity diagram. Because AD is fixed, both the points A as well as D, they will not be moving. A and D both will be stationary. So the points A and D both will overlap each other and they will be stationary. Okay. So let's take the points here like this. So A as well as D, both these will overlap here like this. Next, we will have to know what is the rotation. The rotation speed, you can see it has been given as 360 rpm, but is it clockwise or anti-clockwise? It's telling it is clockwise, which means it is moving like this. So the velocity of B with respect to A, has to be taken. Okay. So the velocity of B with respect to A will be moving to the right side. So let me take velocity in green. Fine. So this is the velocity of B with respect to A. Okay. And the velocity of B with respect to A in the diagram, we'll have to take it on the right side. So we'll have to take it right side here. So this is the velocity of B with respect to A. And the point that we get on the other end is point B. Okay. So the length AB, we will have to use some kind of scale to get this. Okay, some kind of scale we'll have to use to get this. Now, what is the velocity of B with respect to A? That we will be able to find it. Velocity of B with respect to A is given as angular velocity of B with respect to A multiplied with the length BA. Okay. Now, in order to find the angular velocity, we'll have to use the formula 2 pi n by 60, where n value has been given here 360, that is, and multiplied it with BA. BA length, you can see it is 200 mm. While finding the velocity, as I told, we should not be taking the drawing lengths, we should be taking the actual lengths, and that too we should take it in meters. So 200 centimeters. And centi means 1 by 100. Centi means 1 by 100. So that is what we will get over here. So let's quickly calculate the value of velocity of B with respect to A. Let's go back to the calculator and find it. So it's 2 into pi. Where is pi? So 2 pi into n. N value is, you know how much here? N value is given as 360. N value is given as 360. 360 divided by 60. This needs to be multiplied with BA length. BA length is 200 divided by 100. Okay. So we are getting 75.398. When we round it off, we get 75.40. 75.40. This will be in meters per second. So this value we got it as 75.4 meters per second. That's a very high velocity. It's a very, very high velocity. Okay. So the RPM is also very high, so it's okay. We are getting this velocity. Oh, 1 minute. Yeah. Made a big mistake. So the length has been given in millimeters. And milli is 1000. So that's what I was telling. Usually the velocity cannot be so high. We're getting this like that. So 7.54 is what we need to get. So the decimal, sorry, the decimal value is 7.54. This is the value in meters per second. This is the value in meters per second. And a distance of 7 centimeters we can conveniently draw on the sheet. So in fact, let's keep the scale as 1 in that case. So AB length, we will take it as 7.55 centimeters. 7.55 centimeters. Right. So this is the length that we will use in the diagram. Next what we need to do is we need to find the velocity of C with respect to B. So this will be perpendicular to BC. This will be perpendicular to BC. And then we will have to also draw the velocity of C with respect to D. This will be perpendicular to C. Oh, 1 minute. Let's see. Velocity of C with respect to B. This will be perpendicular to BC. That's correct. Yeah. And velocity of C with respect to D, we'll have to draw it perpendicular to CD. Perpendicular to CD. So these directions we should be able to get it from the position diagrams. And we should be able to draw them. Once we have drawn them, we can measure the length in centimeters, and whatever we measure in centimeters, the same will be in meters per second, which will give us the actual velocity. Okay, so let's now go ahead and draw that velocity table. Okay, so first thing, we will just do the notation. Next, let us write down the direction. Let's write down the direction. Once we have the direction, let's find out the value in meters per second, and then drawing length in centimeters. Okay, so one by one, let us do all of these. So first notation is velocity of B with respect to A. Direction will be perpendicular to AB. Its value, we can see we have already found it. Its value is 7.54. 7.54 meters per second. Okay. And the drawing length, as I told, we will take it almost equal to, no, we will just take it as a round off, because we cannot draw exactly 7.54, but we can draw 7.55 centimeters. So this will be exactly between 7.5 centimeters and 7.6 centimeters. Okay, so the first length we will be able to draw on our sheet. So let's come back to our drawing sheet, and below here, let us start drawing the diagram. So the point, let us take it somewhere in the center. So starting point, let us take it somewhere in the center. And as I told, the point which is stationary, both the points are stationary, A and D. So both of them will come here itself. So A as well as D, both will come here at this point. Now from A and D, we need to draw the velocity on the right side. So okay, so we will have to take our protractor, keep it parallel to this like this. Okay, and we will need to draw a light temporary line like this. So this line is perpendicular to length AB, and you will have to take your roller scale. Place it like this. And then you have to roll it. Till it passes through the point. Once you have drawn it, we know that the line is definitely on the right side, so let's take it on the right side. So what should be the length of this? The length of this should be 7.55. So let's take the scale. Once we have the line, let's take the scale, keep it exactly here, and take 7.55, which is, it should be between these two. Okay, so between 7.5 and 7.6, that is the length. Okay. Okay, so this is the point we need. So quickly let us name this point. This point is point B. This point is point B. Okay, so this we will write it as AB. This is written as AB in the velocity diagram. This is written as AB in the velocity diagram. Okay, so AB is the length which represents the velocity of B with respect to A. Next we have to find velocity of C with respect to B. C with respect to B. So this has to be perpendicular to BC. Its value we don't know it. We don't know the value, and here it will be in the diagram. It will be CB. Now CB has to be drawn perpendicular to capital BC. Perpendicular to capital BC. Let's come back to our diagram. And now for BC, we'll have to keep a perpendicular. So let's take our protractor. Okay, let's take it on that side. Let's keep it on this side. Okay, let's take it on this side, and we need to get a perpendicular line. So let's keep a temporary line which is at 90 degrees to BC. 90 degrees to BC. Now we need a line which is parallel to this. We need a line that is parallel to this. Okay, so okay, come on, keep it parallel to this line. Okay, we have to keep it parallel to this line. And then the point is CB. CB means we have the point B. So let's make it pass through B. So we'll take it, make it pass through B. But we don't know again which side the other point is going to come. So let's just draw a line of some length parallel to this, and of some length parallel to that. Once we have drawn that, next we have to estimate the velocity of C with respect to D. C with respect to D. Now this has to be perpendicular to CD. This has to be perpendicular to CD. We don't know its value in meters per second, but we just know its direction. It will be represented as CD in the diagram. CD. So small CD which should be perpendicular to capital CD. So once again, now take your protractor. So let's take our protractor and keep it like this. So let's draw a temporary line 90 degrees. Okay, so this line is perpendicular to CD, and our velocity should be parallel to this. So take your roller scale, keep it parallel to this, then roll it so that it comes and passes through A. Yeah, sorry, A or D, both our points are lying here. Okay, so once you have this, then draw a line like this. Okay, so now you can see we are getting an intersection point over here. So this intersection point is nothing but the other point, which is C. Small c. Okay, so we will need the velocity diagram only till here. Okay, so this is the velocity diagram we need. Okay, so we can darken this. So measuring these, we will be able to get the values. Okay, if you want to want the velocity of C with respect to B, you will have to measure the length CB. Okay, so let's go ahead and measure the length CB. Okay, scale. Okay, so take your scale. Velocity of CB, so we'll have to measure the length CB. So keep it parallel to this, and you can see we are getting a length of 4.1. Okay, The CB length we are getting it as 4.1 centimeters. CB length we are getting it as 4.C. So when we convert, you can see the scale that we took here. Scale was into 1, so it will be divided by 1. So here the value that we get is 4.1 meters per second. 4.1 meters per second. Same way, if you want to find the velocity of C with respect to D, C with respect to D, C with respect to D, we'll have to measure the length CD. Let's go here. Okay. So 6.8. 6.8. So 6.8 will be the length in centimeters. So once again, because the scale was 1, very simply we can just write the velocity as 6.8 meters per second. So these are the velocities we were able to find. So have any of these been asked in the question at the instant when it is and at right angle to AD? Find the velocity of midpoint of BC. Been asked to find the velocity of the midpoint of BC. The midpoint of BC means the point will be here. Let's call it as E, and the length BE. The length BE should be how much? Half of 8, so 4 centimeters. So let's go back to our drawing then and mark that line. So keep it at B, rotate it so that it's parallel to this. Okay, on this we have to take a length of 4 centimeters. So let's take a point at 4 centimeters. So scale work is over. Okay. So this point here is the point E. Okay, and he has asked us to find the velocity of this point E. Fine. So if you want to find the velocity of E, we have to find it from the fixed point A. Okay, so we have to find the velocity of E with respect to the fixed point. Fixed point means velocity of E with respect to A we have to find. So coming back here, we have to find the velocity of E with respect to A. Velocity of E with respect to A. So this we have to find it from the diagram. So in the diagram, this will be represented as AE. This will be represented as AE. But how to find the point E? How to find the point E? So find point E. So small point E is midpoint. It should be midpoint of BC, small bc, midpoint of small bc. So this is how we will get the point E in the velocity diagram. This is how we will get the point E in the velocity diagram. Once we get the point E in the velocity diagram, we will have to join the point, the line AE and measure it to get the velocity of E with respect to A in the velocity diagram. That is the drawing length. Okay, so let's go ahead and do that. Come back to our sheet. We need the midpoint of BC. So we'll have to keep our scale here. Draw it like this. We'll have to keep it exactly parallel to this. And we can see that this length is 4.1. 4.1. So midpoint of 4.1 will be 2.05. 2.05. Okay. Let's take a point. We'll have to take midpoint, mid of 2. So between 2.0 and 2.1. Between 2.0 and 2.1. That will give us the midpoint. So this midpoint is to be called as E. This to be called as E. And once you have the point E, we'll need to join. We will need to join the line AE. We will need to join the line AE. Okay, and we will have to measure the length AE. We will have to measure the length AE. Okay, so AE length, you can see it is very close to 6.9. 6.9. So here we are getting 6.9 centimeters, and because we had taken scale as 1, so this will be 6.9 meters per second. So this is the velocity. This is the velocity of E with respect to A. This is the velocity of E with respect to A. Okay. So that completes our problem. Okay. Not completes. Okay, we were just able to find the A bit. The velocity of the midpoint VBC we were able to find. Next, he is asking the angular velocity of BC and CD. Angular velocities of BC and CD. Angular velocity, you can, it's written as angular velocity omega of BC, and he's also asking angular velocity of CD. Angular velocity of CD. So we know the formula for angular velocity. Angular velocity is radius, velocity by radius. Okay, velocity by radius. So here we'll have to take velocity of B with respect to C divided by the radius. Radius in this case will be the length BC. Okay, and here velocity of C with respect to D we'll have to take divided by the radius. In this case the radius is CD. Okay, so velocity of B with respect to C, we have found it. Velocity of B with respect to C or C with respect to D, both will be equal to 4.1. So 4.1 divided by BC. Now when we are taking BC, we should not take the drawing length. We should take the actual whenever we are finding the velocities. So actual length is 400. So 400 mm we need to take. Okay. So this one is in meters per second. Okay. So what happens here? Here meter and meter will cancel. We are just left with milli. Okay. So 4.1 divided by 400 into milli, and milli we know it is 10 power minus 3, and here we will get it in radians per second. Okay. So let us go back to our calculator quickly and find this. So 4.1 divided by 400 into 10 power minus 3. So this is the value we need. So we are getting it as 41. Okay. So we are getting this as 41 radians per second. That is the answer. Now same thing we have to do here for this velocity of C with respect to D. You can see we have got it as 6.9 meters per second, and the length CD, we should not take this length, we should take the actual length. So actual length of CD is 450 mm. So let's take it as 450 mm. Okay. So once again, just as before, meter will cancel, and we get 6.9 divided by 450. We are left with milli. Milli means 10 power minus 3, and we are just left with the unit radians per second. So let's quickly go over to our calculator and calculate 6.9 divided by 450 into 10 power minus 3. Okay, so we're getting 15.33. So 15.33. This is in radians per second. Hey, I think we made a mistake here. What mistake did I do? Oh, I took it as 100. It is supposed to be 400. Big mistake. Fine. I got it out because 41 radians per second is very big, very large angular velocity with comparison to this, right? So you should be able to find when you're going wrong. Okay, so we were able to find this as 10.25. So it is not 41. It's not 41. This is 10.25 radians per second. So these are the two answers. Okay, these are the two answers. So this is how we should be able to solve the problem. Part of it will be calculation, part of it will be will need to be done exactly as per drawing. Okay. Okay, so like this we'll have to draw it exactly using the drawing instruments, and we will need to draw that. By making measurements and doing the calculations, we will be able to get the final diagram. Okay. So now let's go ahead and do a slightly more difficult problem, because this now we will be taking up a problem which involves calculation of acceleration also. Right. So let's go back to the very first problem that we had seen, which is here. Okay. So a rough diagram also has been given to us. Let's quickly write down what data is given to us. So P1A, you can see that lengths have also been marked here. 300 mm means that's going to be 30 centimeters. So 30 centimeters is difficult to draw. So we will have to take some length which is convenient for us to draw. This length here is 600 mm. As we had done in the first problem that we solved, we will take this as 12 centimeters. Just in the previous problem that we had done, we had taken this ratio. So this we will take it as 12 centimeters. This one by that this one will become 6 centimeters. Okay, so what I'm doing is 600 mm. Okay, so what I'm doing is I'm multiplying it with 2 by 100. Okay, 2 by 100. So this will give us 12 centimeters. Okay, so similarly when we take 300 into 2 by 100, will get us 6 centimeters. Same way do for 360 into 2 by 100, we will get, how much will we get here? 7.2 centimeters. The same way for the last one, this is also 360, so again we will get the same over here. So this is 7.2 centimeters, and this one also has to be 7.2 centimeters. So these are the drawing lengths that we will use to draw our position diagram. So all the lengths are with us. So let's quickly go back to our drawing sheet and draw our position diagram. So let me take a copy of this here, and this problem we will do here in this sheet. Okay. So let's quickly take our scale over here. So this time we will need above a distance of 7.2, and so let's take a scale and take a downward distance of 7.2. so somewhere here at this point we can start trying. Okay, so let's take a reference point somewhere here. Okay, so it has to be more than 7.2 because we will get the diagram above this. Okay, once you have taken this, keep it horizontal. You can take parallel to one of these sides, and then the first line we will have to draw it as 12 centimeters. From this, let's take it as 12 centimeters. Okay, that's going way beyond, so let's take it somewhere in the center. Okay, from start point we'll have to take a length of 12 centimeters. Yeah, so this is the point. So let's quickly go ahead and name the points. So this one we will have to call it as P1, capital P1. This one we will have to call it as P2. Okay, so having got P1, P2, next let's go ahead and draw this length P1A. To draw the length P1A, we will have to take our protractor, but instead of measuring the angle from this side, we'll have to measure it from this side. So use the angles accordingly. So we need the angle to be 60 degrees. Take an angle of 60 degrees. Okay, in your case, of course, you'll have to mark the point and then draw it. In my case, I'm able to draw through the scale, so I'll directly take it like that. and we can see that the length of this has to be equal to 6 centimeters. So let's quickly take our scale. And from this point we need it to be in this direction, and we need a length of 6 centimeters. 6 centimeters. Okay. So we will need a scale. Okay, so let's keep the cell aside. We can see fortunately our length is exactly matching with 6 centimeters. Okay. Let's go ahead and name this point as A. Okay. Now from this point 7.2, and from the bottom point 7.2. Okay. So at this point we will have to take our compass. Let's keep this point here, and then we will have to take a length of 7.2. So let's quickly go here. 7 is here, 7.2 is here. Okay, so take that length, we have to mark it from this point. Okay, so rotate it without making any changes in the length, and then we will have to mark an arc. Okay, something like this we'll have to mark it. Then same length we'll have to take, and mark an arc like this. Okay. Okay. So once you are done with marking, just take a point of intersection. So this point of intersection is nothing but point B. This point of intersection is nothing but point B. Once you have the point B, you can use the scale to connect them. To speed up, I'm just going to directly draw it, but you'll have to use the scale to connect this point. So now you can see that we have got the position diagram correctly. Now for the velocity diagram, we'll have to start making the diagram. Fine. So let's quickly get our table. Okay, let's quickly get our table. So we will first take notation, then direction. Okay, then value. So this value we have to take it in meters per second, and then drawing length. So drawing length we will have to take it in centimeters. Okay, so this is how we will have to get our velocity table. So now let us quickly go ahead and write down all the velocities that we will need. So first velocity that we will need is the velocity of A with respect to P1. Okay, this one has to be, the direction of this has to be perpendicular to length AP1. Value of this, how much will be the value of this? We know the formula for velocity. It is omega into the radius. So for this case, velocity of A with respect to P1, it has to be omega of this, I think, which is given to us. Omega is given directly. So omega has been given as 10 radians per second, and angular acceleration, that is written as alpha, that is 30 radians per second square, and both of them are in clockwise direction. So for finding velocity, we will not need alpha, angular acceleration, we will only need angular velocity. So let's use that angular velocity to find the velocity. So omega into the length AP1. Okay, the length AP1. So omega is given as 10, the length AP1. As I told before also, we should not take the drawing lengths when we are finding velocities. We should take the actual length. The actual length here is 300 mm. Okay, 300 mm. So now milli means 10 power minus 3, which means divided by 1000. Okay. So all three zeros will cut down. So we will get the velocity as 3 meters per second. Velocity we will get it as 3 meters per second. So now how much can we conveniently draw on our sheet? 3 centimeters is going to be very small. So let's just take a scale of into 2, and that will give us 6 centimeters. 6 centimeters. Okay, so the scale that we are using is into 2. So while converting it back, we'll have to divide it by 2 to get the meter per second. Okay, so this is our velocity of A with respect to P1. A with respect to P1. Okay. Next, we'll have to find the velocity of B with respect to A. B with respect to A, the velocity should be perpendicular to BA. Velocity should be perpendicular to BA. Meter per second, the value we don't know actually. We'll have to draw it from the diagram and then find it, measure it in the diagram, and then convert it back. Okay. Then we also need the velocity of B, the point B with respect to P2. Velocity of B with respect to P2. The velocity of B with respect to P2. So this will be perpendicular to BP2. BP2. Okay. And again, we don't know the velocity. We will have to measure it in the diagram, and we will have to convert it back to get this value as well. So now let's quickly go ahead and find this. So we should now come back to our sheet. And with this sheet, we should be able to draw the velocity diagram. So both the points P1 and P2, they are stationary, you can see. So both these points will be overlapping, and they will come at a single point. So the velocity of A with respect to P1, because the rotation is clockwise direction, the velocity will be somewhat in this direction. This is the velocity of A with respect to P1. Okay. So because the velocity is in this direction, we should, while taking the point on the sheet, we should ensure that it is somewhere on the left side. So somewhere here we can take it. Okay. Somewhere here we can take it. So let's take the point here. And what will we call it? So we will have to call it as small p1, and small p2. Small p1. Both these points are going to be overlapping. Instead of taking way over there in the corner, let's take it somewhere here, so that slightly lesser distance is there on the left side, more distance is on the right side, and because it is slightly downwards, more distance has to be there on the lower side. That's how we'll have to start. Okay, so this will ensure that our velocity diagram will not overlap with our position diagram. So now we know the direction of the velocity of A with respect to P1. It will be perpendicular to AP1. So we'll have to take our protractor, place it like this, and then you will have to draw 90-degree line to this. Yeah. Once you have drawn 90-degree line to this, you'll have to take your roller scale, keep it parallel to this. Then you will have to roll it. You'll have to roll it without slipping. You'll have to roll it. Yeah, without skipping. You'll have to roll it and take it here. Now we know the direction of it. The sense is downwards. So from this, we'll have to take it downwards. So let's quickly take a line. And first of all, let's draw a line of any length. Then using our scale, let's measure it. So how much this should measure? This should measure at 6 centimeters. So at 6 centimeters, let us take a mark. Okay, at 6 centimeters, we have taken a mark. So our velocity diagram is going to end here. Okay, what will be the point called? What will be the point called? The point should be called as small a. Point should be called as small a. Okay. Next, we have to find the point small b. We have to find the point small b. So for finding the small b, we will have to draw AB perpendicular to BA and small b P2 perpendicular to capital B P2. Okay. So let's come back here. Perpendicular to BA. So perpendicular to BA. So let's then take our protractor. Okay. So we'll need perpendicular to this. So let me quickly take this should be exactly sure. Okay. So this is the perpendicular line. Okay. So now we need to take a line parallel to this. So take a line parallel to this, and then move it till it passes through point P. Sorry, BA now. BA means it should pass through A. It should pass through A. Yeah. So we'll have to move it keeping parallel. We'll have to keep it parallel till it passes through A. Then draw length, some random length. Let us take it. Yes, some random length. Let us take it. Okay, and then here once again I'll have to draw perpendicular. Yeah, so this line is perpendicular to BP2. Now we'll have to take our ruler scale. Okay, keep it parallel to this, and then you need to roll it. Till it passes through the point P1 P2, P1 or P2. So you'll have to make it pass through this. Cannot. Yeah. Okay. Why is it not moving correctly? There we go. Yeah. So now once again draw a line like this. Okay. So now you can see that the lines are meeting. The intersection point is what we need. Intersection point is what we need. So this is our intersection point. Okay, this is our intersection point. And this point we need to call it as point B. This is the point we need to call it as point B. Okay. So this we need to make it dark. Okay. So this is position diagram. All the visible edges we should make it dark, and in the velocity diagram, whatever lines are representing actual velocity, that should be made dark. Okay. Now we have the velocity diagram. Now by measuring these lengths, we'll be able to get the velocities. Okay. So first let's go ahead and measure them one by one. So first let us measure AB. First let us measure AB. So this, you can see it is starting at 0, and we are getting this as 4.3. So AB length, we are getting it as 4.3 centimeters. So now to convert it back, we will have to divide it by 2. So we get 2.15 meters per second. 1.15 meters per second. Then similarly, we will go ahead and measure this distance. So this we will have to take it as 4.3. Okay, so this one is also 4.3 centimeters. Yeah. So convert it back, we will get here 2.15 meters per second again. So this way we have now found the velocities of both the points, velocities of point B with respect to A, velocity of B with respect to P2 as well. Okay, so velocity diagram is now solved. So what is he asking now? What is he asking? So first he is asking angular velocities and angular accelerations. Wow. Of P to B, angular velocity of P to B. This is what he is asking, and angular velocity of AB is also something that he is asking. Then he is also asking angular acceleration of P to B, and angular acceleration of AB. And the velocity and accelerations of the point of the joint B. Velocity and acceleration of the joint B. So velocity of B we have already found. Velocity of B, by velocity of B, he wants us to find it with respect to the fixed point P2. Okay, that we already found. No? So velocity of B with respect to fixed point is 2.15. Yeah. So this point we have already found. So 2.15 meters per second. This we already found. The next thing is asking is acceleration of joint B. Oh, so total acceleration of B with respect to point 2. This is what he is asking. This will be in meters per second square. So this we need to find. Yeah. Angular velocities will be in radians per second. Angular acceleration will be in radians per second square. Okay. So all these values we will need to find. So wow, angular to do all these acceleration calculations. So before going for acceleration calculations, let us find the velocities now, because we can easily find that. So let's take this. Let's take this. Keep it elsewhere. Let's keep it elsewhere. So this one. Okay, so these two. Let's find it. So this has to be velocity of B with respect to P2 divided by BP2. Okay, so velocity of B with respect to P2, we have just now found it now. This is the value. So 2.15 divided by BP2 is 360 mm. So 360 mm will be nothing but 0.36 meters. Okay, so let's go to our calculator, solve it. So 2.15 divided by 0.36, so we're getting 5.97. Okay, this is in radians per second. Similarly, velocity of A with respect to B will be velocity of angular velocity of A with respect to B will be velocity of A with respect to B divided by the length AB. The velocity of A with respect to B, we have found it in the table. You can see velocity of A with respect to B or B with respect to C, both will be equal to 2.15. So 2.15 divided by the length AB. Length AB is 360. 360 means again we will have to take it as 0.36. 0.36. Okay. So this will again give us 5.97. So both the angular velocities are 5.97 radians per second. 5.97 radians per second. Now let's turn our attention to the accelerations. So angular acceleration. What is the formula for angular acceleration? Angular acceleration will be equal to the linear acceleration or tangential acceleration, tangential acceleration divided by the radius. Tangential acceleration divided by the radius. Okay, so this formula we'll have to use. In order to do this formula, first we'll have to draw the acceleration diagram. All right. So the way we have drawn the acceleration diagram, same way we'll have to draw this. So first duplicate. So let's take a duplicate of this. And what I'll do, I'll just remove the velocity. We will need the velocity now. So let's keep it aside. Let's move it here. Okay. Now we will have to take the acceleration diagram. So acceleration diagram. So for acceleration also, first we will write the notation. Then we will predict its direction. Then we will find its value. We will have to find in meters per second square. And then drawing length. We will have to mark it in some conveniently converted value, which should measure in centimeters. Okay. So let us mark the accelerations. Now, because the link P1A, it is not rotating with constant acceleration. So there will be two components of acceleration for A. Okay. So the first component will be acceleration. Which acceleration? It will be the centripetal acceleration. To write the centripetal acceleration of A with respect to fixed point Q. The direction of centripetal will be parallel to P1A. Yeah. And it will be towards P1. Okay. Value. So centripetal acceleration formula. So I've already told you the formula for tangential acceleration. So let's write it like this. Tangential acceleration is equal to alpha times r, and centripetal acceleration will be omega square divided by r. Okay, so let's take that value. So omega square divided by r. In this case, r is nothing but the length AP1. AP1. So omega of this, it is given to us as 10 radians per second. You can see here it is given as 10 radians per second. So 10 square divided by AP1. AP length is 300 mm. 300 mm when converted to meters becomes 0.3. So this gives us the acceleration. So let's quickly find it out. So 100 divided by 0.3. Oh, that gives us a very big value, 333.33. So this is in meters per second square. Meters per second square. Oh, very high amount of acceleration. Okay, then there will be one more component of acceleration, that is the tangential acceleration of A with respect to P1. Tangential acceleration will be perpendicular to P1A, and because it is clockwise, it will be towards right. Okay, and I've already told you what is the formula for tangential acceleration. Tangential acceleration is alpha into r. In this case, r is nothing but AP1. So alpha has been given to us. Alpha is how much? Alpha is given to us as 30 radians per second square. So 30 radians per second square into 0.3. Okay. So what do we get? We get this point will go over with 0. So 9 meters per second square. Hey, this is okay. 1 minute here. Omega square. It's not omega square by r. It should be omega square into r. Omega square, because acceleration actually it will be v square by r. V square by r or the omega square into r. Okay, so the formula I wrote here is slightly wrong. Be careful. Omega square into r. This is the formula. Yeah, so we have to use that formula over here. So this entire thing is wrong. So the formula should be omega square into r. In this case, r is AP1. So 10 square into 0.3. So we get 100 into 0.3. So 100 into 0.3 is 30. 30 meters per second square. 30 meters per second square. So into 30. Oh, sorry, not into 30. Into 0.3. 0.3. So that gives us 30. Okay. So 30 meter per second square, 9 meter per second square. These are the two accelerations. So now one by one we'll have to draw these accelerations. Oh. For drawing, we will be drawing this as P1 dash to A1. Yeah, this will be a temporary point. P1 dash A1 dash will be the total acceleration. So we will have to take a temporary point in the middle. So that will be P1 dash PA dash. Okay. So this will be representing the acceleration in our diagram. So now 30 30 centimeters are slightly difficult to draw. Here the highest acceleration is 9 centimeters we can easily draw. So let's take the scale as divided by 10. Very simple. Okay. So divide this by 10, we get 3 centimeters. Then this we will take it as p and p underscore a to what is the other point, a dash. Okay. So this we will take it as what? Oh, sorry. So 30, no, this is 9 centimeters, yeah. So this scale won't work out. This will not work out. So maximum is 30. So maximum length that we can easily draw is 6 centimeters. So let us take this as 6 centimeters. So to convert this into 6, what we have done, we have divided by 5. So divided by 5, we should take it as the scale. So 9 by 5. 30 by 5, we get 6. 9 by 5, what do we get? 9 by 5, we get 1.8. So 1.8 centimeters. Okay. So now these measurements we'll have to draw in our sheet. Let's come back to our sheet. We'll have to take a copy of this. Okay. So first length we can see parallel to P1A. So take your roller scale parallel to this, and it will be downwards. Downward length is 6 centimeters. So because it is downwards, let us take a point somewhere here. Okay. So the name of this point P1 dash and P2 dash. Okay, both P1 dash and P2 dash will appear here. Now we'll have to take a line parallel to this. But in downward direction. Let's draw some length. Now let's take the measurement. So what is the measurement he needs? This has to be 6 centimeters. Okay. So let's take this length as 6 centimeters. Okay. Then the next one has to be perpendicular to PA towards right. Towards right means this side. Okay. So next we will just take our this one, protractor. Let's take our protractor. Keep it like this, and we will take a perpendicular line, 90 degrees line. Yeah. So this line is perpendicular. So what is this point that we got? Okay, the point that we got is a temporary point PA. So we will have to call this point as PA, small PA. Okay. Now on this line we will have to take a length of 1.8 centimeters. 1.8 centimeters. So let's take it here, rotate it. So we need 1.8. 1.8 will come here. Only this much. Okay. So now we will get the final point. The final point here is A dash, small a dash. Okay. So by putting dash, we differentiate the acceleration diagrams from the main diagram. Okay. Now we'll have to be careful. Okay. So the the lines for tangential and centripetal accelerations, those must be represented by the dotted lines. Those must be represented as dotted lines, and the final acceleration, that should be represented as the dark line. Okay, let me remove these two lines which were just left out from the extensions. Okay, so now that we have this particular acceleration, next step will be to find the other accelerations which are known. Okay, so what other accelerations do you know? We know the centripetal acceleration of B with respect to A. We know the centripetal acceleration of B with respect to A. Okay, so this will be parallel to BA, and this will be towards the center. So when we are talking about acceleration of B with respect to A, the point A becomes the center, so that has to be towards A. And can we find this? So this is again centripetal. So centripetal is omega square into the length. In this case, the length is BA. And omega also we have to take for BA only. So omega for BA, we have found it now. Omega for AB or BA, both will be same. That is found as 5.97. So 5.97 into BA. BA length is 7.2. Okay. So one minute. BA length, we should not take 7.2. We should take actual length. 360 mm. 360 mm. When we convert, divide by 1000, that should be 0.36. So let's do this calculation quickly. So we get 5.97 times 0.36. We're getting 2.15. We're getting 2.15 meters per second square. 2.15 meters per second square. So this length. So once again, this is going to be to a temporary point. So in the diagram, if you see, we already have the point A dash. So from A dash, we need to go to the temporary point. Okay. So from A dash, we need to go to the temporary point. Let us write it as BA. Okay. So the length, how much we have to draw? We have to divide this by 5. So 2.15 divided by 5. What do we get? Divide this by 5. So we're getting 0.43 centimeters. 0.43 centimeters. So we can take it as round it off as 4. Yes. Once again, this is stuck. Okay. So this line we'll have to take it parallel to BA. So first of all, place this parallel to BA. Parallel to BA. Okay, then roll it. Till you pass it through A. Now we have been told it is moving towards A. That means it has to come on the left side. From this point, it has to come on this side. Okay. And the length of this, how much should be the length? Length should be 0.4 0.4 centimeters. So first let me keep this exactly here. 0.4 means here, right? So there is a very small length. This is a very small length. Yeah. So let us leave it at that. Next acceleration that we can find is centripetal acceleration of B with respect to P2. Next acceleration that we can find is centripetal acceleration of point B with respect to P2. This has to be parallel to B P2, and it has to be towards P2 because P2 is the fixed point. Okay. So this is given as omega of BP2 square into BP2. Okay. So omega of BP2 square, we got it as same as this, no? 5.97. So 5.97 square. Yeah, I missed the square from the previous case. But so we will have to redo it. So let's go back to the problem. This has to be square. So that we are getting 12.8. 12.8. 12.8. Ignore it. 12.8 meters per second square. So this 12.8 divided by 5. 2.56. So 2.56 centimeters we have to take. So not here. So we here. Should be taken here. Yeah. The same way here we have to square it, and BP2 is also same length, no? 0.36. So this also we will get it as 12.8 meters per second square. So here the length will be from B dash to the temporary point BP2. B dash to temporary point BP2. Okay. So this again we'll have to divide by 5. We will again get 2.56 centimeters. 2.56 centimeters. Okay. So let's come back. Yes. So this has to be longer. This has to be actually 2.56. So 2.56 means 2.55. 2.5 and 2.6 in between 2.55 and 2.56. So that point we have to take here. Okay. So the point actually has to be here. Okay. The point has to be here. And the name of this point, what is the name of this point? Dash to BA. BA is the temporary point. BA dash. Okay. Next one is B dash BP2. B dash BP2, and it should be downwards. BP2. Not B dash, yeah, because we don't have B dash, we have P2. So This one is so we towards P2, that means it has to be acting downwards. It has to be acting downwards. How to make it downwards? Okay, so let's draw this downwards, and its length to be 2.56, and it has to be parallel to P2. Okay. So first place it parallel to this. Yeah. Then roll it to here. Yeah. And from here, centripetal acceleration will be downwards. And what will be the value? Value will be 2.56. Okay. So now move this scale. Yeah. So it should be 2.56. It means between 2.5 and 2.6. Okay. That much line is required. Okay. This is also just centripetal acceleration. Now we know that tangential acceleration of this will be perpendicular to this. Okay. So we will have to draw perpendicular to that. Insert perpendicular to this. Okay, like this. Okay, and then we will also have to draw perpendicular to this. Yeah, so this perpendicular we got it. Then we will need also to draw perpendicular.
क्या खाते हो?
ट्यूशन में इधर
आज नहीं खा खा लो क्या तो
Okay, this line. So once again here we got the intersection point. That point is what we need. Okay, so this will give us the final point. The final point being C dash. Okay, the C dash is the final, and these are the tangential accelerations. So the total accelerations will be given as this line and this line. Yeah. So total acceleration is this, or total acceleration, and this is also the total acceleration. Okay. Now let's turn back to what is asked in the question. So he is asking angular acceleration of P2, and angular acceleration formula is tangential acceleration by the radius. So here we need tangential acceleration of P2B divided by the radius, in which case it is P2B. Okay. So this formula, let us keep it. Okay. So let us find that. The tangential acceleration of P2. First we'll have to find this acceleration. Okay. So there are two more tangential accelerations here. Tangential accelerations of b with respect to a and tangential acceleration of b with respect to p2. Yeah. So these two lengths we will have to measure. Tangential acceleration of b with respect to p2. B with respect to P2. There's no point C here. Point C is not at all there, so this point is B dash. Okay, and this is the temporary point BP2. BP2 dash. Okay, so BP2 dash is this length. This length we will have to measure. Oh, lots of X. So this length we'll have to measure. So it is 5.5. 5.5 BP2. So 5.5 centimeters. Okay. So this we have to convert it back. So we will have to multiply it with 5. Huh? So multiply this with 5. 5.5 into 5. So 5.5 into 5. 27.5. So 27.5 meters per second square. This is the tangential acceleration of v with respect to p2. Same way we'll have to find the other one. Okay. So for the other one, the other tangential acceleration is this one. So we will take it. Yeah. That is 2.25. 2.25 or 2.3. We can take it as 2. Sorry, 2.5, 2.6, 2.7, 2.8. 2.8. This one we take it as 2.8 centimeters. Multiply this with 5. So 2.8 multiplied with 5, 14. So this is 14 meters per second square. So these values we should use to find angular. These values we have to use to find angular acceleration. So let me move that down here. So tangential acceleration of P to B, that is 27.5 divided by P to B length. P to B length is 360, so 0.36. So do this. So 27.5 divided by 0.36, 76.4. 76.4 radians per second square. Next, this one we will need tangential acceleration of B with respect to A divided by BA. Tangential acceleration of B with respect to A, we have found it here, that is 14. Yeah, 14 divided by 0.36, the length of AB. Okay. So that gives us 14 divided by 0.36, so 38.9. 38.9 radians per second square. So that completes this particular problem. Okay. So you can see we had to first do the velocity diagram, which we took a scale. Okay, we took a scale and we did the velocity diagram. And with velocity diagram, we were able to find a lot of velocities. once we were done with the velocity diagrams, we had to use the acceleration diagrams. First we had to make the acceleration table, and with the help of acceleration table we were able to make the acceleration diagram, okay, which you can see over here. So for this diagram we will need two sides of the paper. One side maybe it will fit when I move it. You will feel that yeah, we can actually move it, but when you start making the diagrams you have no idea which direction the accelerations are going to be finally going. So it's always a safe idea to just keep enough distances on all the sides so that the acceleration or velocity diagrams are not going to cross over to outside the border of the paper. Okay, so hope this class was effective for you and you were able to learn how to draw the velocity diagrams and acceleration diagrams to solve the particular problem. Okay, so maybe in the next class we will cover up some more problems from your previous university papers, and that should help us to be able to solve this particular unit in a more efficient way. Thank you for now, and we will see you in the next class. Keep practicing. Thank you.